Good morning or good afternoon. Today we're going to talk about the calculus of rotational kinematics. Now, calculus plays a big role when you have some graph like this omega versus time graph. So what's wrong with this graph? Nothing is wrong with this graph except that the curve is not a straight line. So actually that implies that the since the slope of this kind of graph is the angular acceleration, it seems that there are many different slopes. So it seems that there are many different angular accelerations. In other words, the angular acceleration is not constant. If I zoom out, as you can see here, this is the line that determines the slope at that particular part of the curve. And this line, as you can see, it's less steeper and there's a different kind of steepness, a different kind of slope at this part of the graph. So for this kind of graph, we're more interested in finding like what the slope is or what the acceleration is for each time interval. So maybe for this time, for this specific instant of time, we're trying to find out what the slope or the acceleration is at that point in time. Makes sense to ask that question since for each given time, your acceleration is different. So one good question to ask is exactly that. What is the angular acceleration for a specific time? So what's the instantaneous angular acceleration at time t? In other words, what's the slope at time t? Now, in order to do that, we have to draw a line, right? But if you only have one point, then you cannot make a line because 2 points make a line. And if you draw a tangent line, then that's the goal, to draw a tangent line because it is just one line that hits the graph at one point, at this point that corresponds to t. The goal is to find that exact tangent line. But in order to do that, we have to deal with another point because, as I mentioned, 2 points um, make a line. So we add this other point, let's call it t plus h, where h is the gap between these two times. And each of these times correspond to their corresponding angular velocities. For time t, the corresponding angular velocity is omega as a function of t. And for t plus h, this is the corresponding angular velocity. Now we have 2 points, and now we can make a line. But is that the tangent line at time t? No, it's not the tangent line at time t. It's a secant line. So what's the difference between a secant line and a tangent line? A secant line is a line that touches the curve or the graph at 2 points. What we want is a tangent line, a line that touches the curve at only one point. So we have a dilemma. We want a tangent line, but instead we have a secant line. So what can we do? Well, calculus tells us we can make h as small as possible, or we can make these 2 points as close to each other as possible. So for now, we have this slope. The rise is omega th minus omega t, and the run is t plus h minus t. So we just simplify that denominator, and what we are left with is h. As I mentioned, this is not the tangent line we are looking for. We are looking for the tangent line, the line that touches this point corresponding to time t. And in calculus, what we do is we make h as small as possible. And that corresponds with these two times t and t plus h as close to each other as possible, so that these 2 points, these two red points, are as close to each other as possible. So they may be a secant line, but at least the 2 points are as close to each other as possible. And to a certain wonderful degree of approximation, we have a tangent line. And this is actually the definition of the derivative. So what we're actually looking for is the derivative at that time. Because in calculus, and your calculus teacher will explain this better, the derivative of angular velocity with respect to time, that is the slope for this graph, the slope of the tangent line for this graph. And that is the angular acceleration. Right. So the angular acceleration at the time t of a rotating object is the first order derivative of its angular velocity at that time t. And if we do the same process we did with the graph, we can create another graph, position versus time graph, and the slope of that position versus time graph is the angular velocity. But we'll arrive at a similar conclusion. The angular velocity of a rotating object is the first order derivative of its angular position at that time t. If you combine both equations, you will get that the angular acceleration is the second order derivative of position with respect to time. Now, are you still with me? I hope. Now, recall that v is equal to r omega. This is the tangential velocity, and this is the angular velocity. The relationship between tangential velocity and angular velocity. Now, what if our velocity is a function of time, that it changes with respect to time, that it's not constant? Well, that follows that our angular velocity is also changing and is a function of time. So we can get the derivatives, and we can use our previous formulas that we derived using calculus to come up with another formula, the relationship between the tangential acceleration and the angular acceleration. They look similar, right? V is equal to r omega, A is equal to r alpha. So just keep that in mind. Now, how about the area under this curve? If you remember, we said that the area under the curve above the x-axis is the angular position, right? How do we find the area under this curve? The problem with this curve is not like the triangle that we are familiar with, and we know the area to be 1/2 base times height. We don't know the area of this thing. It's a pretty arbitrary shape, and I don't think that there's a formula for this, but we can use calculus. In calculus, what we do is we create rectangles, and we know the area of a rectangle is just the length times width. And in this case, the length is the time interval, and the width is the angular velocity, change in angular velocity. And we add up all of the areas of these rectangles. So you can see it's not that accurate because there are spaces here. How do we account for the spaces here? Then, to make a better approximation of that area, we shortened the width. We tried to make the width as narrow as possible. This was really hard to do. Took me some time to create all of these rectangles, but as you can see, we have a better approximation. The gaps are much smaller, right? So we make the rectangles narrower, and then we add up all the areas of the rectangle. We get, okay, this is the formula. The area is the summation of all the areas of the rectangles, where omega sub t here is just the height of the rectangle, and delta t is just the width. So the omega t times delta t, that's just length times width, or height times length, just the area of the rectangle. And the summation here is just we add up all the areas of these rectangles. And as you may imagine, to get a much better approximation of the area under this curve, we make the width of these rectangles infinitesimally narrow. And you hear that in calculus a lot, infinitesimal. And we replace delta t with the dt because apparently dt makes delta very, very small. This d is a very, very small width. And then we change the sigma into this more. This is like, I just forgot the word. This is my this integral sign is just the sigma on steroids. That's just me. That's just how I think about it. But now this is just the area omega t, and instead of delta t, we now have dt because here we are assuming that we're using rectangles with infinitesimally narrow width. So we have now delta theta is the integral of omega as a function of t dt. And by using calculus, we are now more able to accurately determine the area under this curve. Still with me? Okay, so for derivatives, just um, take note that in general in physics, derivatives are for instantaneous rate of change. They are for getting the slope of the tangent line, and they're usually associated with division. Integration is for getting the area under the curve. It's for accumulation or adding up a bunch of rectangles, and it is usually associated with physics formulas that involve multiplication. And for a position versus time graph, if you get the slope, you get d phi dt. Don't tell me about the meaning of the area under a position time graph. There is a name for that, but that doesn't belong to general physics, and I think there's no real physical significance. None that I've known of. None that I know of. And for omega versus time graph, we all know that the slope is just the angular acceleration, d omega dt, and delta phi is the integral of omega t dt. So the area under this curve is just the change in angular position or the displacement. For acceleration versus time, the only important formula is the change in omega. So the area under the curve is the change in angular displacement. Not the angular displacement itself, but the change in angular displacement. Now don't tell me what the meaning of the slope is for an acceleration versus time graph. There is a name for that. It's the jerk, the angular jerk, but we're not really interested in that. Okay, let's go to some examples. Number one, an airplane propeller is rotating at 1,900 revolutions per minute. How many seconds does it take for the propeller to turn through 35 degrees? Okay, this is a very trivial question. It doesn't really need calculus to solve this because in the first place, there is no acceleration for this problem. It's just the propeller rotating at a constant angular velocity of 1,900 revolutions per minute. So what we're doing here, we're still using calculus, but it's an overkill. I'm just showing you this to illustrate that calculus works. Question is, how many seconds does it take for the propeller to turn through 35 degrees? You want to answer this? You can pause this video. Okay, I will now proceed first by converting, oops, sorry, nagkabali-bali na ang pag-show, but I'm just gonna convert 1,900 RPM to rads per second. So 199 din siya. And I draw this graph just to show that it's constant for an omega t graph. the graph is a straight line, kay constant raman iyang angular velocity. 35 degrees, I converted that into radians as well, so 0.611. And now I'm using this formula to calculate the area under the curve. Omega t dt, integral of omega t dt from 0 to t. And I'm not really interested in getting the angular displacement or the area under the curve because it's already given to be 35 degrees or 0.611 rad. But I'm still using this formula because I'm looking for t and it has t in it. Omega t, as I said, is 199, just a constant. But so I put it there, and if you know the rules of integral, you'll get 0.611, which is our angular displacement, is equal to 199t evaluated from t to 0, or 199t minus 199 times 0. Mawala naman to siya. So what is left is 100. Let me do that. Oh, Kailin Laligan. Okay. Minus 199 times 0. I hope you remember your rules in integration. What's left is just this, and we divide both sides by 199. We get 0.000307 seconds. The final answer. I hope you're still following me. I hope this works. Oops, number 2. A bicycle wheel has an initial angular velocity of 1.5 rads per second. So I think there will be an acceleration now because we have an initial angular velocity and it's about to change. This initial velocity is about to change. So if angular acceleration is constant and equal to point, that's a good sign. Constant. Woo, equal to zero point 0.2 rads per second squared. What is its angular velocity at time 2.5? So we're looking for the angular velocity at time 2.5. Through what angle has the wheel turned between t equals 0 and t equals 2.5 seconds? Let me just graph the angular velocity omega versus time graph. Um, it will look something like this because the acceleration is constant, starts off with initial 1.5 and goes up to this unknown final velocity, right? This is what we're looking for at part A, and we know this time to be 2.5. Okay, that's good. Now we can do kinematic equations or that graphical analysis, but in this particular problem, we are going to use calculus to solve this problem. Now, my goal right now is to come up with a function, an equation for omega as a function of time. How do we define this line as a function of time? Well, we can use this equation y minus y1 equals m times x minus x1 to create a linear equation, linear function, omega t. Here, our y1 is the initial y, that is 1.5. Our slope is 0.2 because that's our acceleration. Our x is that we leave it there. And our x1 is 0 because um, it's at t equals 0 where 1.5 is. So we just convert y here, of course, our omega. So omega minus 1.5 equals zero point 0.2, and our x is the time, t minus 0. And manipulating further, we now have a function of omega as a function of t that is expressed as zero point 0.2 t plus 1.5. We will use that. We now have this wonderful equation which represents the omega as a function of time. We will use that for letter B. Now let's go to letter A. For letter A, I realized we can use the acceleration versus time graph. And as you can see, for the acceleration versus time graph, our graph is a straight horizontal line because our acceleration point 2 is constant. Now we can calculate the area under this line, and that represents the change in angular velocity. And the formula is the integral from alpha t dt. As I mentioned, our alpha is a constant, so we just write point 2 because our alpha is a constant. And our integral is evaluated from 0 to 2.5 seconds. Since angular acceleration is constant, alpha t is just a constant, point 2, yeah. So our delta omega is zero point 0.2 times t. I hope you know how to do that from the rules of integration. Evaluated from 2.5 to 0, and what we are left with is zero point 0.2 times 2.5 minus 0, and our delta omega, we expand that to omega f minus omega I because we're interested only in omega f. And we know omega I is 1.5. We transfer that to the right side of the equation here, and when we finally are left with just numbers, we can now solve for omega f. It's 2 radians per second. Okay, so I ran out of space. So for letter B, through what angle has the wheel turned? So this one we already have had solved for this omega t. We now have the function for omega t, the equation omega as a function of t is equal to zero point 0.2 t plus 1.5. And now we can use this formula, which is for calculating the delta theta of an omega versus time graph. It's just the integral of omega t dt. Now, omega t is this one, so we put that in and we evaluate from 0 to 2.5. I'm sure you know how to integrate this function. It's 0.2 t squared over 2 plus 1.5 t, evaluated from 0 to 2.5. Let me pause for a moment. Doesn't this look like omega I t plus 1/2 at acceleration times squared, right? So we just derived the kinematic equation. Substituting 2.5, we have this minus 0 because everything else is 0 for this evaluation. And we are now left with numbers and we get 4.375 radians. Okay, let's just pause to appreciate our work. This is sample problem number 3 and I basically ran out of time. But if you're willing to accept the challenge, you can solve this on your own. This is easy enough, but I just ran out of time. So I hope you learned something today. Buragadali ko, but I hope you still learned something. Thank you.